Welcome to today's tutorial. My name is Engineer Okelwe Obaga. I want to do it. Okay. Hi friends, welcome to today's tutorial. Today we want to do the determination of shear force and bending moment diagram for a trapezoidal uniformly varying load. Now we have the load on the board. We have a span of about 60 meters. And there is the shape configuration of this particular varying loads. Now the intensity of the load is 20 kilonewton per meter. Now let's determine the shear force and bending moment diagram of this particular simply supported beam. Now the first thing we are going to do, we are going to obtain the reactions. Now when we draw it, we are going to have the bending moment, the free body diagram of this particular beam as this, have it as this. This all let's call here RA, let's call here RB. Okay. Now, if we calculate this, if you look at the shape is a trapezoidal shape. So you can say sigma Fy is equal to the area of the trapezium, and this is area of the trapezium is half. Calculate the length. Here is 10. Here is the entire length is 20. So it's going to be A plus B times height. A is 10. B is 13. Sorry, B is 16 times the height is the intensity of the load intensity, which is 20. So if we do that, we're going to have that our sigma Fy is equal to, sorry, all right, so we are going to be working on this. Now, if we draw this is a free body diagram of this expression. Here is 3, here is 3. So we are going to obtain the reactions at the support. So we'll start by saying sigma Fy is equal to 0. Sigma Fy 0, we have Ra plus Rb to be equal to the area of this trapezoidal shape. The area is 1 over 2 times A plus B times height. A is 10, B is 16. Height is the intensity of this load, so say times 20. So if we do that, we're going to have Ra plus Rb to be equal to, this gives us 160. This gives us 26. So this becomes 260 kilonewton. All right, so that is the total vertical reaction. Now, the next thing we are going to check out is looking at the beam. You can see it is symmetrically loaded on the simply supported beam. So what it means is that the reaction will be the same. So if we divide this beam into two equal parts, we're going to have the same reaction here and here. So if Ra and Rb are going to be the same, and we can now say, meaning Ra is equal to Rb. So if we divide it into two, the reaction Ra and Rb will be of the same value. So because of the symmetrical arrangement of the load, so we have, let's say, 2 Ra, when Rb becomes Ra, becomes 260 kilonewton. All right, so we can have our Ra now to be 130 kilonewton. Okay, so having gotten Ra, the next thing we need to do is to obtain the moment expression and shear force expression for each of the load zone. Now, if you look at the board, we have three basic load zone. We have the first load zone, which is a triangle, the second load zone, which is a rectangle, and the third load zone is a triangle also. So quickly, we are going to get the load zones for each of these particular load. Now, let's start by taking the first load zone. Remember, we intend to determine the shear force and bending moment diagram, and also we'll also obtain the maximum bending moment. All right, we'll obtain the maximum bending moment for this particular beam. Okay, so now we having this. let's start from the first load. So let's say 4, 0 is lesser than x, and x lesser than 3. That is the first load zone we're going to consider. Now, what we have as a shear force expression, the shear force expression becomes, remember how we used to do it? If you look at the previous videos, you have a good understanding of what we did when you are taking moment expression. Now we're cutting between this particular range. Just cut between the range. Let's call the section we are cutting, let's call it 1, 1, 1. You can call it whatever you wish. Now, when you cut through, you are going to have a vertical reaction, which is our shear, and you are going to have a moment which is anti-clockwise. That will be the internal moment, which is also a function of x. Now, this is x, value for x to this point. So this is the first thing we are going to see. Now, apart from this, remember that we are cut between this particular load zone. Now, this is a triangle. Remember, when you cut between it, you are going to have, let's just make a sketch of it. Let's just make a sketch of it. Let's assume we are cutting somewhere here. You have this. This goes in this direction. So if you complete it, let's assume that this is a 1, 1. This is a 1, 1. So here is 20. Okay, now we've cut between it, and this is what we have. We've already called here our x. Okay, so now we have a problem. We need to obtain the intensity at this point. If you look at it, the intensity increases as it goes to 20. So, but there's a particular load intensity at this point. So let's get it. We quickly use the similar triangle properties. Remember that the total length of this is 3 meters. All right. So if we use similar triangle, we have to triangle this triangle 1, which is this one, and the second triangle is the entire full triangle. So we're going to have a similar triangle. The distance here is x over the total distance 3, equal to intensity of the small triangle is, let's call it k, over intensity of the entire big triangle. And if we do that, we'll have that our k becomes equal to 20x over 3. So k becomes 20x over 3. So that is the load intensity at that point. So we have that to be 20x over 3. So what we'll do, let's since we've known that, let's clean off this. Let's clean it up. So we know now that here we have 20x over 3. So we have here to be 20x over 3. All right, so that is the load intensity at that point. Now remember that the support reaction, we've gotten it to be 130 kilonewton. So that one is here. So quickly, let's get the shear force expression. We quickly do the summation, algebraic sum of forces, sigma Fy to be 0. If we do that, we're going to have positive forces, 130 kilonewton going up, negative forces, which is representing the triangular load, coming down. So we have shear force. So we're going to have them as 130 positive, triangular load negative. So our negative 1 over 2, the area of the load, the distance, the breadth of the triangle is x. The height, which is intensity, now becomes 20x over 3. Okay, so it becomes 20x over 3. Now our shear force expression, which is also negative, is coming all equal to what? 0. So our shear force expression, which we're interested in, f of x, becomes this, and we'll have it as 130 minus this. We go, we have 10x. Sorry, I think we just calculated the area. All right, so we have it as 10x squared over 3. All right, so that gives us the shear force expression for this particular load zone between 0 and 3. So now the next one, let's get the moment expression for this load zone. So if we do that for the moment expression, we have always gotten this. So we can say the moment of this particular shape is the area times the distance from the centroid to our point of interest, which is our section 1, 1. So we can write the moment expression by saying m of x become equal to distance from here to here, taking moment about section 1, 1, we have from 130, we have 130x minus, okay. Now let's take moment for this load. Now we have this load to be what? The area of the load is this. We've got it is the area. So the area of this load is 10x squared over 3. We've gotten it before. Remember, this entity represents the area of the load. Now this area of the load times the centroid. The load is going to be acting, becomes a point load acting on somewhere here. Now for a triangular load, we'll have a triangular load. The centroid of that load is at a point such that from this point here, we have it as 2/3 of the total length, while this point is 1/3 of the total length. So if the triangular base is, for example, is 3 meters, like we have in this case, it becomes 2/3 of 3 from that center of the load down to your left hand side. 2/3 of 3 will give you what? Will give you 2. While the other side is 1/3 of the entire length, which is 1/3 of 3. That will give you 1. So if you add 1 plus 2, it will give you the original length of the triangle. So that is how to obtain the centroid of the triangle. So now we know that. So this case now becomes easier. The total load is known. Now the centroid, what will be the centroid? We're interested because we're taking moment about section 1, 1. So the load is acting now. We've gotten the load acting at the center. From the center to this point is 1/3 of that distance. And the distance in question is x. So we're going to have x over 3, which is 1/3 of the distance. So if we take the moment expression for this point, we'll have it as 130 x minus, this becomes 10x raised to power 3 over 9. So that is the moment expression for this zone. So now we've got the moment expression for this first zone and the shear force expression. Now let's go over to the second zone. If you look at the second zone, is a rectangular load from that zone. So we're going to cut a section from there. We have this will now become C4. Let's write the C4 for 3 meters, between 3 meters and 13 meters. What we'll have as is what we'll have. So I'm cutting a section already. Let me cut section 2, 2. Shear force F of x is here. Moment expression also is here, M of x. So we already know here to 3 meters. All right. Here is 130 kilonewton. kilonewton. So yes, 130 kilonewton. Yes, 3 meters. Here remains 10 meters as usual. All right. So now let's write All right, now let's write the shear force expression for this particular load zone. So if we do that for the shear force of this zone, we are going to, sorry, let's redraw this so that we can have a clearer picture of it on this other side of the board. So this is what we are interested in. This 2, this section 2. Here is a shear force, internal shear force, and here is a bending moment. Remember that here is x down to this point. Remember that here is 3 meters, and so on. Okay. Now let's calculate the shear force expression. This is 130 kilonewton. All right. So for this zone, between 3 meters to 13 meters, we have this. Remember the load intensity here is 20 kilonewton per meters. So now let's write the shear force expression. We'll say F of x is equal to 130. There's no need of taking summation of x and y. Summation of x means summation of y. Let's just write it straight off. We have this. This is also a trapezium. So what will be the area of this shape? Remember that area of a trapezium is half base times a plus b times height. These are a. Our a in this point becomes x minus 3. Okay. So from this point here down to this point become x minus 3. Let's call that point our a. So this become x minus what? 3 plus b. Our b in this case become the total length of this, which is x, times our height remains 20. So we can have our f of x as this 130 minus. If we add up a plus b, which is this, will give us a 2x. It becomes a 1 bracket 2x minus 3 times 20. Okay. So if we continue in that form, we'll have that f of x becomes equal to 130 so we'll have this to be minus 10 bracket 2x minus what? 3. Okay. So that's what we have as the shear force expression for this particular case. All right, so you can see we've been able to use the area of the trapezium to obtain that. Now, what will be the moment expression? Similarly, we'll have the moment expression as m of x equal to, here becomes 130 times x. 130 times x. Now, 130 times the moment about section 2. Here, let's calculate the load. Now, what we should have done, or what we can do, is to obtain the centroid of this trapezium, so that by the time we calculate the load, it's going to be the load times the centroid to section 2, centroidal distance to section 2. But let's see whichever one will be easier. Alternatively, we can decide to obtain it individually. We can take the load of this triangle, multiply it about the centroidal distance to section 2, or we can take the load, we can take the load from this point and multiply it to section 2. So we're going to have 2 loads that we're going to use, meaning we're going to have 2 sections. Okay. So let's do it this way. If we intend to calculate the total centroid, it's going to be another method, but let's do it this way. So we're going to get this one. If we do this one, the area of this one becomes half base times height, which is 1 times 3 times 20. That is the load. Now we'll get the center from this point to here. So let's start with the first triangle, which is half times base. Base is 3 times height. Height is 20. So this is the load multiplied by the centroidal distance of that load to the section 2, 2. So the centroidal distance from this point, remember I told you for a triangle of this nature, from this point is 1/3. Here is 2/3 of the total length here. Okay, so in this case now our total length is 3. So we'll take 1/3 of 3 plus 1/3 of 3 is where we're interested in the distance. So from here down this point is 1/3. Is 1/3 of 3, which is 1. Okay, so here is 1 meters. And from here now we have x minus 3. Okay, so if we do that, we're going to have 1 plus x minus 3 as the centroidal distance of that load. So 1 minus s minus 3 will give us x minus what? 2. Okay, that's the first one. Then we have that for the rectangular shape, we'll have it as the load here is 20, so we'll have 20. So we'll have 20 times the distance is s minus 3. So once we do that, this becomes a load. This becomes a load. Now, what is the centroid of this load to this point is just x minus 3 divided by 2. So it becomes x minus 3 divided by 2. So for write the moment expression here, we'll have it as m of x equal to 130x minus this 10, which is 30. So it becomes 30 bracket x minus 2. While this point will go, this side will have it as, if we open the brackets, it becomes, this cancel becomes 10. So we have 10 bracket x minus 3 all squared. All right. So this is what we have as the moment expression for this particular beam for this zone. Now the next of them, we are going to take the second load zone, and the second load zone is for 13 meters to 16 meters. That is the second load zone. Now, if we do that, we are going to have it as, let's draw the free body diagram. So let's assume this is where it is. So all right, so this is how we're going to have it. Remember that here remains 20 kilonewton per meters. Here's 3 meters. Here's 10 meters. And here is unknown. So let's call here, we'll have here our 130. So value for x here, x comes this way. Now let's call this one section 3, 3. Section 3, 3, we have the shear force expression. We have, we only have a problem with this particular triangle. Let's take the shear force expression. We have it as f of x equal to 130. F of s equal to 130. So we have 130 minus, let's take this load. Yes, 1/2 times 3 times times 20, that is the load, minus, we have this point to be 20 times 10, that is the load. Now these other points, these are triangle, minus this triangle, remember, is having the shape of a trapezium. All right, there are two ways we can handle this. But before we do anything on this particular portion, let's take out the portion out of the system so that we can see it clearly. Let's take out the portion. You can see it clearly. This is what we're interested in. All right, so there's the portion. Remember that here is 20 kilonewton per meters. Now let's divide this section into two portions. Let's call this 1, let's call this 2. Now if you look at portion 1, it's a triangle. Portion 2 is a rectangle. All right. Now we need to get the area of this and this. And once we get their respective area, we can take their respective centroidal distance to this section, which is our section 3, 3. Okay. Now the first thing we need to do, if you look at the intensity of this triangle, it increases towards this point. So we need to obtain the value for this point. Remember that the total length of this triangle, total base, is 3 meters. So we can look for the distance where we already know here this point to be x minus 13. That's what we have here. Okay. This whole point is x minus 13. So here is x minus 13. All right. So if this point is x minus 13, that is where we need to obtain. So we can easily obtain this area in terms of x. So remember, in terms of x, let's take the triangle, similar triangle. By similar triangles, we have this small triangle. Now this small triangle becomes what? If this whole place is 3 and here is x minus 13. So if this whole length from here to here is 3 meters and from here to here is x minus 13, all we need to do to obtain this point is to say 3 minus x minus 13. So become 3 minus x minus 13. That gives us this particular portion. So if we do that, here become x, this minus this minus x plus 16. All right. So this gives us minus x plus 16, or 16 minus x. All right. So this portion becomes 16 minus x. This portion becomes x minus 13. So if we go by similar triangle, which we are going to do now, by similar triangle, we'll have this as 16 minus x over total length of this shape is 3 meters. So I have 3 meters. All right, equal to the whole of this to this point is this point we do not know. Let's call it k. So we can say the intensity k over total intensity, which is 20. So we can have it as equal to 20 bracket 16 minus x over 3. All right. So that will be the value for k at this point. So once we know the value for k, we can calculate the load of this portion 2. So that will help us to calculate. We already know. So if that is the value for k, now the whole of this height here is 20 kilonewton per meter. So this particular height is known as this. So for us to get the real height of this portion of the triangle, remember that the total intensity here is what? Is 20. We've gotten that of this portion 2. So for us to get the remaining portion 1 with the intensity of portion 1 separately, it becomes the total intensity of the full triangle minus the total intensity of at this point k. So So it becomes 20 minus k. All right. So if we do 20 minus k, becomes 20 minus 20 brackets 16 minus x over what? 3. All right. So this is what we have for it. So we can decide to solve it so that we can obtain a value for it. All right. So now let's look at what we've gotten. So for minus 20, from 20 we'll minus this. If we multiply this, we're going to have 20 minus. All right, so this portion which is here, we have it as this particular triangle. Have it this way. Is a triangle. The intensity here becomes 20 minus k. All right, while we have this portion, which is a portion of the rectangle, to be k. Okay, so these are the 2 points we have in this particular shape. Remember, each of them has their centroid, their length, their base to be x minus 13, x minus 13. Okay, so we are going to pick it from there. Look for the value for k here. The value for k here becomes this becomes k becomes 6.666. All right, 6.666 becomes 16 minus x. That is our k there. 16 minus x. Y here becomes 20 minus our k, which is minus 106.6656. Okay. 0.66x. So let's take it to 4 decimal places. So this is what we have. And for this load, let's finish it up. We have it as 20 minus. This becomes 106.6656 plus 6.6666x. All right. So if we do that, we have it as 86. So the 86.66656 plus 6.6666x. All right. So this becomes the intensity of this triangle, sorry. Why we have this one to become the intensity of the rectangle. This one is for the intensity of the triangle. This one is for this portion is the intensity of the rectangle. So now we have these 2 figures which we are going to use to obtain. Now these are the intensities. So for us to get the shear force, of course, remember that the shear force is the area of this particular shape. So we have the intensity for the triangle to be this. So it means this intensity times the distance. So it's going to result to some sort of a quadratic equations. Okay, so let's go ahead and fix it. All right, let's go ahead and fix it. So we're going to have here minus. Now the intensity of our triangle, let's start with our triangle. We have it as 6.6666x minus 86.6656. Okay, that is for our triangle. So remember, the area of the triangle is half base times height. So the base in this case here, like we see, the base becomes x minus 13. So x minus 13. The height, which is our intensity, is this entire entity. Okay, so that's what we have. Now the next one is the triangle. The triangular portion, the area, the load acting on this point, it becomes the intensity of the triangle times the distance covered by the triangle, which is length times breadth. So the length in this case is x minus 13. We assume the breadth to be our intensity. So intensity becomes K. So and that value for K is 106. It becomes 106.666. All right. 106.66 minus 6.666x. All right. That is intensity times the area, the distance covered by that load is x minus 13. All right, so this gives us the shear force expression for this particular load zone. So if we want to simplify it further, we'll just go and expand it. Okay, so x becomes, let's work out this here, we have 1, so this becomes 30, so it becomes 130 minus 30. All right, so if we work x minus 13 bracket, this gives us 3.3333x minus 43.332. 43.332. Okay, so let's continue to simplify it. Then on this other side we have minus, we have minus 10, we have minus 106.666 minus 6.6666x. All right, because this is x, and here we have x minus 13. So this gives us the expression for the shear force if you wish to expand it, but looking at what we have, there is no need because that appears to be the last zone of this particular problem. So expanding it will be of no significance. We can plug in values of s from 13 to 16 into this expression and get whatever shear force we intend to get along this line. All right, so we can leave it this way. Now let's move over to the next one within this load zone, which is the moment expression. Now the moment expression, we'll start with this zone. You remember taking the moment about this point. We take a moment about this point. This becomes, can pick this one. This load acts at the centroid here. So if this load acts at the centroid, here becomes 1/3 of 3. So here is 1. Here is 2. Okay. So if here is 1, this point is 1. Here is 10. And here is x minus 30. So if you calculate the total distance, it becomes x minus 2. So this load becomes, we start with say 130. Let's do that of 130 times x minus this load, which is the load here we'll discover that is 30 brackets. The distance becomes x minus 2. Okay. Then let's start with this other one. The load here is 200. So the centroid becomes, you divide 10, which is this distance to here, over 2, it becomes 5. 5 plus this particular s minus 13 will give you what? Will give you 8. So here becomes minus 200 bracket x minus 8. Okay, that is the moment, that is the expression there. Now the last is the last zone, which is we've gotten before, little bit complicated. Now remember what we did, that we have the various intensity for this zone. For that of triangle, we have that of the triangle to be this value. So we have this value as, we have it as open bracket, let's say 6.6666x minus 86.6656. All right, that is uh, for the rectangle. So let's say the rectangle will have half times uh, the base, which we know as x minus 13, times this area times the centroid to this point. The centroid to this point is, so this becomes the area. The centroid of this rectangle to this point is 2/3. So from here down to 2/3 of this point. So it becomes 2/3 of x minus 13. All right. So that becomes the centroid to that point. Now, let's look at the rectangle itself. The rectangle, we've gotten it to be our k from what we did the other time. And we'll have it as this. So we're going to have it, the rectangle, to be this. So we'll have it as, we say minus 106.6656. All right, 106.6656 minus 6.6666x. All right, that is intensity of this rectangular portion times the area, the distance, which is s minus 13, times the centroid. The centroid is s minus 13 over 2. So the centroidal distance from the center of gravity of this rectangle to section ZZ becomes x minus 13 all over what? 2. So this gives us the what we call the moment expression for this particular zone between zone 13 meters to 16 meters. So this gives us the expression. So with this equation, you can plug in the value for x from this 13 meters to 60 meters. Once you plug in values for x, you will have the moment of any point along that particular range. All right, so now I've gotten the bending moment expression. The next thing we are going to do is to determine the maximum moment. So from here, you can take tables for f of x and tables for m of s, and you can get bending moment at any point within each of these boundaries that we've stated in the board. Now, the next thing we are going to obtain is the shear force. Now, take note. So let's rewrite this expression and make it more simpler. We'll have it as m of x equal to 130x minus 30 x minus 2, we have 200 x minus 8. All right, so we have this. Now take note, this we cancel this. Okay, so we'll have here to be all right, so we have two of these. So we have x minus 13 squared all over 3. Okay, so bracket x minus 13 squared over 2. So this becomes the expression for moment for this section. Now, like I said, we may not need to begin to calculate all we need to do is to plug in values into it and get the moment along that particular range. Now, in determining the maximum moment, which of this zone is going to produce the maximum moment? Now, if you look at the board and look at the beams, by symmetry, most likely to occur at the zone between 3 to 13. That is where the maximum moment will occur. And this maximum moment will occur at a point where shear force is 0. So for us to obtain the maximum moment, if we don't want to use symmetry, all we need to do, identify the load zone that is likely to produce the maximum moment by looking at the load configuration. Remember that this load is a varying load intensity, has varying load intensity. So if you want to do that, you can say f of x between load zone 3 to 13, let it be 0, and look for x. When you look for x, you will know the distance, the point along x where we will have the maximum moment. All right. So the maximum moment will occur at that zone between 3 meters to 30 meters. All right. So, but if you want to do that, you can try it out to see and look for s at that zone. Equate f of x to be 0. Once you do that, you have the values for x, value for x that will produce the moment. So once you have that value for x, substitute the value into the moment expression for that particular load zone, which is load zone 3 to 13, you will have the value for the maximum moment. So let's see who can do that and obtain. But if you are not sure, like other kind of load zone, once you are able to identify the load zone that will most likely produce the maximum moment by visual inspection, equate the shear force expression to be 0 and obtain the value for x. Substitute that value for x into the moment expression for that particular load zone, and you will have the value for the maximum load zone. Now, take note that from load zone 0 to 3, we have a triangular load, and triangular loads normally produce curves that are cubic. You have cubic parabola curve, while from 3 to 13 meters is a rectangle. So a UD here, uniformly distributed load at that point for that zone. And that load will always produce a quadratic curve, all right, which is not cubic parabola. Now, the same thing goes with the last zone. We also produce a curve that is of the same equation as that of the first load zone. So take note while drawing the curve. So now, if you look at it, the maximum moment will occur at the center of this beam because it's symmetric. It's a symmetric load. So if we divide it into 2, the maximum moment will occur at the point 8 meters away from the left hand support or from the right hand support, whichever direction you are picking it from. So that maximum moment will give us the value for x at that point is 8 meters. If you want to try it, you can substitute it into the shear force expression we have in load zone 3. Put it into the shear force expression that we have in load zone 3 to 30. You have the maximum moment. So let's see. Let's get that value and let's just draw the curve and the bending moment diagram and shear force diagram. Okay. And also take note that also for load zone 0 to 3, for the fact that the curve, the bending moment diagram for that zone will be a cubic parabola, what it means is that the shear for that point will be a quadratic, is going to be going to carry a parabola, not cubic parabola this time, a normal parabolic curve. And also the same thing happens to load zone 13 to load zone 16. So the same thing will happen. So when drawing the diagram, take note of this particular point. Why for between point 3 to 13, we'll have the shear force diagram to be a straight line. It's going to be a straight line from that zone. So it's going to run straight from x equal to 3 meters to s is equal to 30 meters. So that is how I go. So let's draw this. But first of all, let's obtain the maximum moment. All right. All right. So let's obtain the maximum moment. So for maximum moment, we can say for maximum moment, consider zone 3 meters to 30 meters. So we can say that the f of x, we've already called it 3. If you want to check it, you will see that f of s equal to 0. If you come to that, look at it here, 130, this is the expression. 130 minus 10 bracket 2x minus 3 equal to 0. So if we solve this mathematically, we'll have that x is equal to 8. Okay, we have that s is equal to 8. So x is equal to 8 meters. All right, so that is all we have for x. Equal to 8 meters. Now what will be the maximum moment? The maximum moment expression, we put in x into this expression to obtain the maximum moment. So if we put x into this expression, we will have 8. So let's do that and see. This is the expression. Let's do that and see. If here is 8, if here is 8, let's see what we have. So if we plug 8, we have that the maximum moment, m maximum, becomes 10, becomes 130 times 8. 130 times 8 minus 30 times 6 minus 10 times 25 squared. So eventually we'll have everything to be 610 kilonewton meter. So this 610 gives us the maximum moment for this particular beam. All right, so when we draw the shear force and bending moment diagram, you will see the values. All right, so let's draw the shear force and bending moment diagram quickly. All right, so you can see the bending moment diagram. Now, this brings us to the end of this lecture. If you do enjoy this tutorial, do well to subscribe to our channel for more updates for our new videos. See you in our next class. Good day.